And now we're going to move to the next speaker. So we're very happy to have Andy Strominger from Harvard, who is going to tell us about celestial holography. Andy?
Okay. Let's see. Okay, share screen.
Share screen, yeah.
Does that look good?
Perfect.
Looks perfect. Okay. And what time how much time do I have now? There was so much discussion.
All right. No. I'm keeping it very on time. So you have 30 minutes and then 10 minutes for questions.
30 minutes and then 10 minutes for questions. Okay. So I'm going to talk about an approach to holography in flat space called celestial holography. Okay, what's happened here? Sorry. What? Oh. Okay, there we go. So the black hole area entropy law, that the entropy of a black hole is the area horizon over 4 times Newton's constant, is the primeval holographic relationship. It says that the number of degrees of freedom of the black hole scales not like the volume of the black hole, but the boundary of the volume of the black hole. So understanding this formula for black holes with near horizon anti-de Sitter regions, in which we've had a spectacular success over the decades, went hand in hand with understanding ADS-CFT holography in anti-de Sitter space. And so one might guess that understanding black holes in flat space, where the information paradox takes its most striking form. You start out with a pure state, you make a black hole, and all the energy went to the maximally mixed state, will go hand in hand with understanding holography for quantum gravity in asymptotically flat spaces. For example, this island rule entropy, one might hope in the flat space context to derive it from some holographic formulation of quantum gravity in flat space in the same way that one derived the island rule entropy formula in ADS space. Now, if you want to find a holographic dual, one of the first things that you better do is figure out what all the symmetries of the problem are, because the holographic dual and its partners better have the same symmetry. Now, thanks to the subleading soft graviton theorem and the subleading soft graviton theorem and all the new subleading theorems we've learned about in the last few years, we now have a better picture of this. And I think the picture of the nice way to think about this was drawn almost 20 years ago by Du Bois and Solodukin. And what they did was they said, hey, let's just write flat space as a non-compact compactification. So the compact direction is usually noted tau, it goes this way, over a sequence of anti-de Sitter, Euclidean anti-de Sitter up here, in the future and the past, and a de Sitter region in the space-like region. Let's write it as a non-compact compactification, decompose the wave equation that way, and then we've got wonderful three-dimensional anti-de Sitter space whose holography we understand in insane detail, and we can use that to uplift to a holographic description of Minkowski space. And the hologram should live at the boundary, and the boundary we call the celestial sphere. Now the problem is there's 2 boundaries. There's one in the future and one in the past. But one of the things that we've learned in the last few years through the soft theorem is that the conformal structure on these boundaries, this is supposed to be a lock and chain, are locked together, so we can view it as one sphere. There's one conformal structure, and there's a canonical way to identify, it's actually antipodal, to identify points on the future sphere with the past sphere. And of course, these symmetries, there's a lot of symmetries here, and much more than just the supertranslation symmetries. And they greatly constrain the black hole formation S matrix and will induce correlations between the Hawking radiation and the quantum state of the black hole. And this was partially analyzed in Hawking and Perry with Sasha, other Flanagan and Nichols, Busso and Prati, various people. And also I think there's a lot of resonance here with the talk that Suvrat just gave. So the basic idea is that you start with an S matrix and written in a momentum space basis, and you just simply rewrite it in a conformal basis. In other words, instead of using momentum eigenstates, you use Boost eigenstates. So the conformal group, the global conformal group, is nothing but the Lorentz group. So writing things in Boost eigenstates is just like what we would do in two-dimensional conformal field theory. And due to the subleading soft theorem, which after a long line of manipulations, which I've given many talks on, you learn this thing has also not just a global, but a local conformal symmetry. And so the basic idea is that there should be some kind of holographic duality in which the S matrix in Minkowski space is written as some kind of correlation function on what we call a celestial conformal field theory. And we call it celestial conformal field theory because it has some peculiar properties that are not characteristic of an ordinary conformal field theory. Now, the conformal symmetries are not the only symmetries that act on here. There are the supertranslations, for example, and they have the peculiar property of relating an operator of dimension delta to an operator of dimension delta 1. So the correlation functions on this theory, it seems like they obey way too many constraints, that there shouldn't be any set of correlation functions which obey all these constraints, but we know that there is, because we can construct them through reverse engineering. So I want to explore here. So, flat space holography, it's kind of like ADS holography, at least in this construction. It's as close to ADS holography as it could be because it uplifts the ADS slices, but there's going to be a lot of differences. And the celestial conformal field theories, they have the same conformal symmetry, but they're different from ordinary conformal field theories. And so we'd like to try to understand what their properties are. And so far, almost all the discussion, of which there's been kind of a slow boil over the last 5-10 years. The conformal fields theory story, maybe it's been going for 3 or 4 years. It's been mostly bottom up. Let's take a field theory that we understand, rewrite it as a conformal field theory. The left-hand side in this duality defines the right-hand side. And it's a little bit like Brown-Hainaut. I mean, ADS really started with Wan's paper, but Brown-Hainaut, it was a top-down from string theory approach, but Brown-Hainaut had a bottom-up approach where they just said, assume an assistant quantum theory of gravity on ADS3. We can see there should be some conformal symmetries. That paper wasn't read very much. Beautiful paper, it should have been, but it wasn't read very much. It could have been used to develop some notion of holography on ADS, which didn't depend so much on the details of string theory. So that's the approach we've been finding. Now, a top-down approach from string theory, that is an intrinsic construction of a conformal field theory, is not ruled out. And in fact, we're saying that the S matrix is computed by a conformal field theory on the two-sphere. Well, that's, of course, what you learn on page 1 in any textbook on string theory. You compute conformal field theory correlation functions on a two-sphere, and you get the string space-time S matrix. So could those somehow be the same two-dimensional conformal field theories? Well, Stieberger and Taylor showed that they are, in fact, in a certain limit where the boost weights get large. And I was also in this regard very taken by Rajesh's talk, in which he talked about the relationship between the conformal field theory on the boundary of ADS and the conformal field theory on the string world sheet. and showed that they were same because of this lunar mature localization, the localization moduli to the lunar mature subspace. And there was also Givian, Kudasov, and Seiberg, who talked about the relationship between current SL2C current algebra on the world sheet, uplifting to the Versaro algebra of AJS3 in space-time. One might also less ambitiously try to do this for the CHY string in 4 dimensions. And I want to say, for those of you out there looking for a hard problem, if somebody gives an intrinsic construction of a conformal field theory that defines a bulk quantum gravity theory in Minkowski space, that is a very major breakthrough. It's a hard problem, but it doesn't seem ruled out that it's possible. Along the way, we encounter many string-like structures, and it kind of suggests that much of what we know about string theory, in this talk, we are only going to use things which are known to be true of all theories in nature, which contain gravity and gauge theory. And nevertheless, we are going to be found that the structure that underlies it all, if you assume of ultraviolet completeness and so on, looks an awful lot like string theory. And this has been a recurring theme. Now, what is the same and what is different about these theories? Well, they both have conformal field theories and ordinary unitary rational, celestial conformal field theories and ordinary unitary rational conformal field theories. There's 2 Versaros, there can be current algebras. The collinear singularities, which have been studied a lot in gauge theory and gravity, are the same thing as OPE singularities in on the world sheet, and we're going to have more to say about that. The representations are different. Ordinary conformal field theory, you usually have discrete highest weight representations. More exotic things are discussed, but that's the usual thing. Here we have a continuous family of complex highest weight representations lying on the unitary principal series. Various things. And the biggest thing is that there are these infinite dimensional symmetries, the super translations, the subleading soft theorem, subleading soft symmetry in gauge theory, the subleading soft theorem in gravity, which we're trying to understand how much power they have in constraining the scattering. Okay. So a lot of cool stuff has happened. There's a beautiful enriched structure, a coherent overarching picture is not there. So I can't give you one. I'd love to. We're sort of groping around looking for ultimately an overarching picture, I suppose would come from a top-down construction. Instead, I'm going to just share some tantalizing tidbits of what we've learned. Okay, so what do I mean when I say this conformal basis? Well, usually you would write an amplitude as a function of the moment, and I'm suppressing spin variables and so on, and actually I'm mostly going to talk about massless particles. All of this remains true, and it's beautiful the way it remains true for massive particles and spinning particles, but it's simplest to discuss the massless case. And what you do is you trade the momenta for an energy omega n, the 4 momenta for its energy omega n, and for the point z to which the momentum points, there's an explicit formula for it, to which the momentum points on the celestial sphere. So if you have a null particle, it will with these momenta, will end up at this coordinate on the celestial sphere. For a massless particle, it goes to the future hyperboloid, and then we have an interesting integral. Instead of this simple omega integral, we have an integral over the bulk to boundary propagator in H3. But for that reason, we're only going to talk about massless particles. They also have a conformal weight, H and H bar, which depends on their spin and lies on this principal continuous series. And Pistersky and Shao showed that these were a complete basis of orthonormal. So you can go back and forth between this basis and orthonormal. The complete basis of renormalizable wave packets up to these subtleties at 0. Now, lambda is actually, L naught generates a boost, lambda is the boost weight, so lambda is the Rindler energy. So these are closely related, and I'm working with that with Adam Ball and Noah Miller. These are closely related to Rindler modes. Okay, so you take this ordinary momentum space amplitude, you do its Mellin transform, and you're left with a function of z, and these give you operators. These can be thought of, this looks like a correlation function on the sphere, and these operators can be thought of as being labeled by weight hk and hk bar. And that correlation function, that defines the correlation function, which we write in this form as an object on the celestial sphere. So we want to study properties of those correlation functions. So they've been computed in a lot of cases. I won't review that here. One interesting thing I want to say is that in endpoint already at tree level, if you have a bad theory, like Einstein gravity, the celestial amplitudes don't exist because the integral of even the tree level interactions over all energies diverges. You need a theory like string theory with some exponentially soft high energy behavior. So that seems like a very nice thing. The moment you say celestial amplitudes, the fact that it has some good UV behavior is baked in, because the theories without, classical theories without good UV behavior don't have a corresponding set of celestial amplitudes. They exist for all theories which are either renormalizable or finite, but not others. In other words, we're not free to discuss a lot of the swampland. Now, I'll be brief here because Andrea gave a beautiful talk on this. So the operators are labeled by their conformal weight, and it's interesting to ask. We know in ordinary conformal theory, amazing things happen when one of the conformal weights goes to 0. You get a concurrent current which generates interesting ward identities. That happens here. It's related to the conformal soft theorem. And in fact, we proved it using UV regulator, as did Andrea and this group, using UV regulators, showing that you get what looks like the standard current algebra ward identity. It should be a QK here, sorry. Standard current algebra ward identity. And this is surprising in the conformal picture because the conformal things involve modes of all energies. So the intuitive argument that you have this soft theorem because the mode is so in energetic space, because the mode is so spread out that it doesn't see the details of the interaction, isn't true there. Still, it's forced on you by some kind of argument having to do with the behavior under boost weights. The celestial stress tensor is also an example of that. Now, super translations are more interesting. For gravity, gravitons have this. Now notice that H minus H bar is always 2. So this is the conformal weight of a graviton on the continuous principal series. And something special happens when lambda goes to 0. And in fact, this operator is holomorphic in correlation functions, but it has the peculiar factor, the word identity tells us that, has the peculiar feature that when it acts on another operator, then it shifts its conformal weight by 1. Now, in fact, one thing I meant to say is that part of the problem in an ordinary conformal field theory is is figuring out what the operator content is, depending on how the theory is presented to you. Here we're given that. For every stable particle, which there might be very few, it could be there's only the graviton in some theories. We know we have at least the graviton and the electron and the photon. There might be very few completely stable particles. For every such particle, there is a continuous complex spectrum of conformal primaries labeled by H and H bar. So therefore, it makes sense to say that we map from an operator of one weight to another point in that same spectrum. That wouldn't make sense in the discrete series, for example. Now, how does this constrain scattering amplitudes? So this is a beautiful story which we just published at the end of last year. How does this affect, operator product expansions, which are the same thing as collinear singularities? So a lot of work has gone into computing these, but it turns out that they can be computed very simply using the symmetries. So just from dimensional analysis, we know that if we take two gluons of weight H1 and H2 of positive helicity, the coefficient of the third positive helicity gluon has a 1 over Z1 minus Z2 times some arbitrary function of the weights. And what we're going to show is that all the symmetries we know completely fix that function. So translation invariance, just commuting both sides with translation, shows that these weights obey a recursion relation where you shift both of the two arguments by a half. Now there's something else called the subleading soft symmetry, which was proved by Francis Lowe and other people in the late 50s. And that subleading soft symmetry also has a global piece, or also a piece which concentrates near the two operators, and it gives you this recursion relation, which relates these weights. Now it's known that together with some boundary condition at infinity, that these two recursion relations are exactly what is needed with exactly these factors to completely fix the form of the 3-point OEE function, OPE function, and that is fixed to be just the beta function. And that agrees with more tedious direct calculation of the Mellon transform of the collinear singularities produced in momentum space. And in fact, all the leading graviton-gluon OPE collinear singularities, and that most interestingly includes the subleading soft symmetry, which turns a graviton into a gluon and vice versa, are so determined by the symmetry. How far we can go with this to get all the subleading OPEs and so on is yet to be seen, but it clearly is imposing a big constraint on the theory. So finally, I want to mention a paper that is to appear with Nima and Monica Pate, who's a junior fellow, and Ana Clario, who sadly is leaving us for Perimeter, and which hopefully will appear soon. And there we sort of combine the ideas from the amplitudes program and from what we're doing. They're clearly very close and asking many similar questions. We try to look at the analytic structure, and also we learned some very interesting thing about infrared divergences for these celestial amplitudes. So first of all, we want to assume what most people believe to be true, maybe it's even proven somewhere, that in quantum gravity at very high S, that all amplitudes die exponentially. Now, this is due to the fact that there are exponentially, because at high amplitude, you can make a black hole with entropy S, and therefore there are exponentially many states that contribute to the final cross-section, so every exclusive amplitude should be exponentially small. Near S equals 0, we can expand this amplitude in terms of some functions of z. Here, we're just at tree level. We'll do quantum theory on the next page. And these are coefficients in the low energy Wilsonian effective Lagrangian. And they obey very interesting positivity constraints, which have been shown in this work on the EFT hedron by Arcani, Hamed, Huang, and Huang. Now, the celestial amplitude, which is the Mellon amplitude of that, S is the square of omega, so I can integrate over S if I take care of the factors of 2. You can integrate over poles or log cuts. The only place you can get a divergence, assuming the exponential softness, is at the origin. And so that tells you that this, this object, the only divergence, this object is meromorphic in the delta plane, except for poles at tree level, simple poles at even negative integers. So the problem of studying the analytic structure of scattering amplitudes is in a new and apparently very simple form. We just have poles regularly spaced, regularly double integer spaced on the negative axis, and moreover, there are constraints among those poles. What happens to go when we go to the quantum theory? And here, again, I want to stress, we're not assuming n equals 4. This is true of any amplitude in any consistent, fully consistent quantum theory of gravity. So the ultraviolet behavior still should be exponentially suppressed, and divergences in A tilde all occur only at the IR. They're still meromorphic, though now we can get higher order poles from logs. Now, infrared divergences with logs appear now in exclusive amplitudes. And of course, this is a big bugaboo in ordinary quantum field theory because you have to introduce a regulator and in order just to define the amplitudes. So now let's just do but the form of these logs is controlled by the soft theorem. And let me do QED, though the story for gravity is even prettier, but longer to write down. There we find that all the infrared divergences are absorbed into a prefactor, where the prefactor involves the cusp anomalous dimension and the log of the ultraviolet cutoff multiplied by, well, the Wilsonian cutoff divided by the ultraviolet cutoff. Now, if you transform this to the celestial sphere, now it's not at all obvious that the Mellon transform of a single object, a product of two objects in momentum space, is the Mellon transform, the product of two Mellon transforms. But it is, except that you must renormalize the dimension of the, so it transform is the product of two transform, and one piece is an infrared safe hard piece, and the hard piece involves only a shift in the boost weight, an ultraviolet divergence shift, but it can be absorbed into the shift or the boost weight of the hard particle. And the soft particle is actually of the form of a current algebra correlator on the celestial sphere with level gamma. And this is a very standard thing to see in conformal field theory. Whenever you have a current algebra, the correlation functions divide into two pieces. Okay, so first of all, it's very nice that we can clearly extract the infrared safe information in this context. But even nicer is that A hard is nothing but the infrared safe scattering amplitudes with Faddeev-Coolidge dressings in their unique conformal primary form. Now, one of the things that bothered people about Faddeev-Coolidge dressings is that they involve an arbitrary function of the momentum, and so there are infinitely many of them, and they form an overcomplete state. That does not happen in the conformal basis. Conformal basis conformal invariance allows only a unique function that function would not have been considered by Faddeev and Kulish because pieces of it, it's not an energy eigenstate, and pieces of it have infinite energy, as do all conformal basis states. So Faddeev Kulish would have thrown that out by putting some arbitrary cutoff at high energies. We don't need to do that. Similar things occur for gravity, where this charge here becomes the translation operator, and this prefactor isn't just a number, it's an operator which acts on the infrared safe matrix element. Now back to so I'm very happy about this, that there's a way of thinking about an S matrix, which doesn't have IR divergences in it. And of course, part of the reason I'm happy about it is that just in order to ask if the black hole S matrix is unitary, we have to have an S matrix. Otherwise, there's not even a question to ask. And it's well known that if you take a generic S matrix, even E plus goes to E minus, and you integrate out the soft sector, what's left is completely incoherent. So if we want to carefully keep track of quantum information, we need some kind of S matrix, and we need to say something about the soft particle. Now, there's a lot more interesting structure that has come out of this analysis, but there'll be a paper out soon, hopefully. Finally, to add to,
Sorry, Andy, you have 1 minute.
Okay, to add to and echo what Shiraz said in his beautiful talk, various things like this that Nima has been saying, a really sharp problem is what's the most general form of the graviton 4-point function. And Shiraz had a whole bunch of constraints which greatly limit. There are more of them. Subleading soft symmetry is not imposed, or I don't think supertranslation or conformal invariance have been imposed. One thing I'm excited about is the possibility of putting all these, many different people in the community have been thinking about this from different ways, and possibly if we put it all together, we can get a unique or nearly unique 4-graviton scattering amplitude. And the million-dollar question is, does that amplitude, how unique are the ones that the only ones we know, namely the ones that come out of string theory. So finally, the reformulation of Minkowski space as a collection of correlators on the celestial sphere is leading to novel insights, and there's a lot left that we have to understand. Okay, thank you, Nastya.
Thank you. Let's thank Andy for the great talk. And now we have 8 minutes for questions. So could you please raise your hand? There are a lot of discussion in the chat, but if I don't see any. There are a lot of people discussing in the chat. Would some of you like to ask a question? Okay, Dan Harlow.
Yeah, I think the issue, so the question was about where the singularities are located in the correlators. In particular, there seem to be singularities away from coincident points, which is not standard for Euclidean CFT. So do you have any comments about those kinds of singularities?
Yes, that of course is a very important point. And so in momentum space, of course, all scattering amplitudes are either 0 or infinite. They're 0 if the momenta don't line up, and they're infinite if they all line up. Here, one of the singularities of momentum conservation remains, and that's a delta in the real part of the conformal cross ratio. And so a question is, how could you get such a thing in a conformal field theory? And we have a possible answer to that question. We don't know if this is how it goes. I'm working now with Anna Reclario and Alex Atansov. We've done a conformal partial wave expansion. Nastya has also done such things, and a conformal block expansions. And this singularity is a direct result of translation invariance. And the conformal blocks are not translationally invariant. They're mapped into one another by the act of translations. And so there's something that we'd like to call, usually you talk about SL2C blocks. There's something that we'd like to call Poincare blocks, though we're not even very sure what they are yet now. But anyway, it appears that the delta functions come, you have things like z over z bar to the n. You add those over all values from n from plus to minus infinity. That's what you're forced to do to implement translation invariance. And when you do that, that turns into a delta function. Delta of the imaginary part of z is the sum from n goes to minus infinity and infinity of n over n bar. So you can get other kinds of infinities in conformal field theory when you have infinite number of fields. Here, the infinite number of fields are the sequence of fields that you get from infinite numbers of translations. And these divergences are no more difficult to deal with than they're 1/4 as difficult to deal with as the divergences that you get in ordinary momentum space quantum field theory, though they appear very novel from the point of view of two-dimensional conformal field theory.
Shiraz?
Hi, Andy. Great talk. I wanted to ask about, you have this way of getting a clean finite S matrix for QED and for gravity. The problem of finding finite S matrices and non-trivial interacting conformal field theories seems sort of similar but more difficult. And I was wondering whether your methods might lead to a prescription for finding clean S matrices and non-trivial interacting field theory, conformal field theories as well.
You mean ones without IR divergences?
No, ones with, so if it's a conformal field theory, presumably it always has IR divergences in it. So say n equals 4 Young mills at lambda equals 1.
Okay, well, yeah, so I mean, I'm very optimistic, though I have to say even my close colleagues don't share my optimism, that techniques like this can get us infrared finite, because I think we've understood conceptually where infrared divergences come from. They are the penalty you pay for trying to compute things which are zero due to conservation laws. If you don't violate the conservation laws, you don't get any infrared divergences. Now, I'm optimistic, and indeed we've already done this work on color memory and so on, that we can find infrared finite amplitudes even for n equals 4 non-abelian gauge theory. And indeed there's a very beautiful algebra. The superconformal and the conformal transformations tie in with the leading gauge transformations to give you the subleading gauge transformations. And so it's a very tight structure that there aren't going to be many ways around.
Sorry, and one follow-up, if I may, Anastasia?
Yes, go ahead. Yeah.
These finite S matrices, the finite S matrices that you have, they some sort of Kuczkowski's rules, do they obey unitarity cutting rules by themselves? Even in the case of QED.
You broke up, Shiraz.
Yes. Do your finite S matrices, do they obey unitarity cutting rules like Kuczkowski's rules?
That's a very good question. I imagine that question, I don't know, let me say, I don't know the answer. I would imagine that question was addressed in some form, which will be very hard to read, way back in the 70s. when Fadeev and Kulish were doing this kind of work. And there's some question of whether the intermediate states will be dressed or not. And if they're dressed, what do you know, how do you think about it?
Thank you.
Okay, unfortunately, we have to really move to the next talk. So let's thank Andy for the great talk again. And now we're gonna move to the next speaker, Samir Marthur from Ohio State, and he's gonna tell us about the Vickrey hypothesis. Samir?
So I'm just trying to share screen now.